Good morning, everyone. Today we are looking at 4-1 exponents. The I can statement is I can evaluate expressions with exponents. This is an Edpuzzle video, which means you have questions on it, as you already know. At the very end, we have a couple of notes to finish up on, as we didn't finish these notes the other day. So, quick review of what we talked about last week. Exponential form would be a number, which we call a base number, raised to an exponent. Which tells us how many times that base number is going to be multiplied together. Our example would be letter A here. We have 4, which is the base, 2, which is the exponent, and that is going to be the same as saying 4 times 4 because the base is multiplied together twice. Quick review for you on that. Power is a number produced by raising a base to an exponent. We did talk about the fact that if you use 4 squared, the power is going to be 16, and that is totally correct. However, we said that it's wrong to say 4 raised to the power of 2. It should be 4 to the exponent of 2. That is actually incorrect. It can be called 4 to the power of 2 or 4 to the exponent of 2. So just to clarify that, we talked about it last week. That was incorrect. It is okay to say 4 to the power of 2. Moving down to writing exponents, if you have the long expanded written out form of 4 times 4 times 4 times 4, and you're to write it in exponential form, you just again take 4, which is your base, and raise it to the power of 4 the number of times it's being multiplied together. That's also shown with variables, and then on number 5 we showed it with variables and numbers. Just be very careful on a problem like number 5 that if you're going to write it without a symbol, you put the number before the variable. So 5 to the third b squared is totally acceptable. What's not acceptable is b squared 5 to the third. That would be incorrect. The only way to make that correct is so wrong. You could go b squared times 5 to the third. You could go b squared parentheses 5 to the third. In this case, there's no negative, so it doesn't really matter where the exponent is, which we'll talk about in a second. Number A, our letter A, 5a explains that. Exponential form, 6 to the third on number 3, expanded form, written all out, and then the power, which again is still going to be the answer, as well as you can say 6 to the power of 3 here, 6 to the exponent of 3, but technically your answer is also called a power, which is the evaluated form of 6 to the third. Remember what we talked about with negatives, 7 and 8, very important here. If you have negative 2 to the power of 2, you are only attaching that exponent to the 2, not to the negative. So you're going to square 2 and keep that negative attached. If you have a parentheses, then you are going to, with an exponent, then you're going to square everything inside the parentheses, including the negative. So in this situation, it would be negative 2 times negative 2, which is equal to 4. In this situation right here, as we talked about in class, it is 2 times 2, which is 4, and then you attach the negative on. And the negative can actually technically be called a negative 1. Moving on, order of operations and the diagonal formula. So number 9 is pretty self-explanatory. You follow order of operations once you plug in the numbers for the variables. And then the diagonal formula is something you're going to need to know. 1/2 times n squared minus 3n, where n represents the number of sides of a shape. And this is where you're going to add your notes because we don't have anything here. So I want you to add number 11, and we're quickly going to draw a square, and we are going to evaluate the number of diagonals in a square. First of all, it's important that you know a diagonal, and you can add this to your notes wherever it makes sense. A diagonal would be a line connecting non-consecutive vertices. A line connecting non-consecutive vertices. So a diagonal in a square shape, so I'll draw my square again, would be here to here, here to here. Then obviously when we get over to this vertex, we've already have our diagonal drawn. You can't count a diagonal when you have 2 vertices connected because that actually forms a side, and we talked about that last week. So for a situation like a square or a rectangle or a quadrilateral parallelogram, you're simply going to plug in for your formula 1/2 n squared the number of sides the shape has. So this shape has 1, 2, 3, 4 sides. So 4 squared for n minus 3 times 4, again for n, big parentheses, and then solve. So we've got 1/2 16 minus 12. Kind of going through order of operations, but not really. 1/2 times 4. 1/2 times 4 is 2. So our answer is 2 diagonals. Obviously, you could draw that out pretty easily, but when you get into larger shapes like dodecahedrons or multiple-sided shapes, you are going to want to use the diagonal formula because then you just plug in the number of sides and you will easily be able to find the number of diagonals. To prove that point here with our last note, we're on number 12. If you have a multiple, this is a really ugly shape, sided shape, you probably aren't going to want to try to connect all diagonals and count them because it's going to get messy. So there's just from one point, and then we go to the second point, and it also is going to take a lot of time. Notice how messy it's getting already. And then we go from our third point, and so on and so forth. So what you're going to do is you're just going to count up all the sides and plug it in for n. So we've got 1, 2, 3, 4, 5, 6, 7. Looks like this is an octagon. So we have 8 sides. You plug in for your 8 for n, and I'll let you do that on your own, and you get the number of diagonals that that shape has. I want you, before you are done with your notes, to fill in the cheat sheet idea. Do that on your own. You're not going to work with your buddy because it is quiet work time right now. So for number 4, you have the cheat sheet idea that you must add, and we'll talk about that in class on Thursday. Good luck.